We're going to start. There we go. Perfect.
Okay. Hi, everybody. It's a great pleasure to introduce Dr. Lai-Sang from Courant Institute of Mathematical Sciences, New York University. She's currently also distinguished visiting professor at the Institute for Advanced Study, Princeton. Dr. Young is specifically recognized for her work in the theory and applications of dynamical system, and has made contribution to mathematical physics and computational neuroscience. Dr. Young obtained her PhD in mathematics from UC Berkeley in 1978. She has held faculty positions at various universities, and since 1999, she's been the professor of mathematics and neural science at NYU. She's won numerous awards over the past 2 decades. Recently, in 2020, she was elected as a member of National Academy of Sciences, and she's the recipient of the 2021 Jorgen Moser Lecture Prize for her deep contribution to the theory of non-uniformity of hyperbolic dynamical systems. Fascinated by the brains as a large and complex dynamical system, Dr. Young has expanded her research to include theoretical neuroscience, so great for us, where she's currently leading a multi-year project to build a biologically realistic computational model of the visual cortex. Today, she'll be walking us through her recent work on a thalamocortical model of the monkey visual cortex. And I'm very excited to hear your talk, and thank you so much for joining us today. One last thing is that please feel free to put your questions on the chat. And if you have a burning question, so I guess you can just, go ahead and ask it. But most question will be for the end of the talk. Thank you.
Okay, so should I, thank you for the introduction. Should I try to share now? Okay.
Yes, please go ahead.
Okay.
Looks good.
So I need to move some of the things out of the way so they don't cover my page. Okay, so should I get started? It's okay.
Sounds good.
Okay, so hello everyone. Thank you very much for inviting me. So, so for the last several years, I've been trying to understand the visual system of the macaque monkey, which is very similar to our own. And I've been trying to understand it through theory and through computational modeling. So this is part of what I would like to share with you today. Okay, so let me start with just a little bit of neurobiological background. Okay, so this obviously is a head of a human and not monkey. So the visual information comes in through the retina. Your optic nerve takes it to this knee-like structure called the lateral geniculate nucleus, LGN. And from there, in one synapse, it goes to the back of your head, which is where the visual cortex is located. Now, so the visual cortex is further divided into regions, V1, V2, V3, V4, and so on. And V1 is the entry point. It's called the primary visual cortex. It is far and away the largest and the most complex of all the different cortical regions. Okay, so simplifying a little bit, its primary function is to identify edges at specific spatial locations, but it actually does many other things. Okay? So the others cortical areas have more specific functions. V4, for example, is they don't exactly look like that. This neural sheet is all crinkled up, so they actually are hidden. So people have spread it out and drawn it as though it was flat, but it doesn't really look like that. Okay, so V4 is associated with with geometric shapes and forms. V5 is with motion and so on. But since everything comes through V1, what V1 doesn't see, you basically don't see the rest of the way. So a lot of the processes are initiated in V1, although they're completed later. So for purposes of this talk, I will be talking about, well, it goes through the retina to LGN and then to the V1 and then to higher cortical areas. And my talk will be focused on this part, LGN and V1. And so just a couple of facts that we need to know. One is that in this part, there are actually 2 distinct visual pathways. There's a magno pathway, which we use primarily at low contrast. It's extremely sensitive, and it's It doesn't have color. It doesn't see details that great, but it's activated very, very easily. And then there's the Pavlo pathway where we use more for color and for details. Okay. So one last thing that's in the overall picture that's important is that it's not just V1, but this entire neural sheet is divided into layers. And this is a picture of V1 under a microscope. You can see the layers actually quite easily. Most of the connections are lateral, so you can see that they go like this, but they're also interlaminar connections. So this is kind of the overall picture that I will be relying on. Okay, so now about the model that we have been building. This was done together with Bob Shapley and Mike Hawken, who are neuroscientists, primarily experimentalists, and Logan Charaka is postdoc. Okay, so here the model goes like this. Okay, is the primary focus these two pieces. This is LGN, and this is the input layer to V1. So it's really focused on LGN and the input layer to V1. So this is the light intensity map, which doesn't have to be a grading. I've just used it to symbolize whatever information is coming through. And I've skipped over the retina to go directly to LGN because the retina and LGN actually are quite similar for the part that I'm modeling. Okay, and unfortunately I can't just stop here because there is some kind of feed-forward feedback loop with another layer in V1, and this layer is very hard to model. So the modeling of this layer is not so great because it consists of a very large number of cell types and it interacts with other parts of the brain. But the modeling of these two parts is intended to be realistic. In the sense that we actually model the neurons, the wiring, we follow neuroanatomy, and I will illustrate a few points of wherever possible, and I will try to illustrate a few points of what I mean by that. So for a start, in this input layer of V1, we use correct cell density where each layer, so this whole thing is about 1 point, in the real visual cortex is measures at about 1.5 millimeter by 1.5 millimeters. But it's really more normal to look at how things project to the retina. And so everything is in degrees. So 1 square here corresponds roughly to 1 square here. So in other words, 1 square here is kind of like a quarter the size of the moon, just to give you a sense of the size of the model. Okay. And so in this picture here, that consists of 9 squares or hypercolumns. It consists of about 40,000 conduction space integrated and firing neurons. 80% of them are excitatory and the rest inhibitory. And here's the connectivity. So what we have done is we have tried to get information on connectivity and axon length and so on as best we could from the literature whenever it's available. And not all of it is available, obviously. So for example, we use the peak really close to the neuron. The peak E to E connectivity is quite sparse, it's 10 to 15%. The other ones are much denser. This is according to experimental measurements where we can find them. Okay, so this is how it looks. Okay, so if you pick an E neuron at any place, there's nothing special about this location. I just put it there, and taking into consideration things like cell density, axon length, and so on, we estimated that it would be connected to about 200 neurons, which we randomly drawn. So these are the neurons that are connected to that one. They are randomly drawn. In one square here is the same as 1 square there. And for I neurons, they get many more E neurons. And this is this one. The black dot can be either E or I. And the blue dots are I neurons. They are more compact, the axons are shorter, and we try to follow that too. And in layer 4C alpha, there are no long range connections, making it, there are very few long range connections, making it much easier to model than the other layers. So this is an overview of what the model looks like. And so what's the goal of our model building was that we're trying to understand the dynamic mechanisms underlying vision. Now, our visual system is not like a camera. We don't really pick up, information pixel by pixel and then just report it on. And we pick up some information, we extract some information out of that, we suppress, we enhance, we process it in different ways. And how does that all come about is part of what I would like to try to understand. And the way I'm going to do it is that I'm going to view the whole thing as a dynamical system, which it is, because it changes, evolves with time, and there are moving parts. So what it is that given partial information on the dynamical system, and the partial information being the structures that we know about, the neural anatomy and the physiology, is very partial. There's lots of things that we don't know. Okay, and many examples of what I think of as input-output relations, namely experimental data. Okay, when you do an experiment, you know what you put in, you know what comes out, you don't know what happens in between. So given some kind of overall some structure that we know about, together with a lot of input-output relations, what we try to do here is to reverse engineer the dynamical system. And once we've done that, to try to analyze it, and then to try to discover the mechanisms. And of course, we go back and forth with the data to make sure that we are not doing anything really funny. Okay, so what's the current status of the model is that most of the basic visual properties of the input layer have been replicated. Most, of course, is in quotation, and basic should also be in quotation. Okay. What I mean is it's not one or two, but it's a bunch, right? So for example, firing rates, that's the one that's easiest that's the one with a lot of data on. And it's not one thing, it's firing rate under many different situations. Spontaneous, when driven in different ways, when it's driven optimally or not, and so on. So this is actually a large group of situations where we try to conform to experimental data. There's contrast response, there are tuning curves, there's orientation tuning, spatial frequency tuning, temporal frequency tuning, direction selectivity, there's simple and complex cells, there are gamma rhythms, and so on. So we have tried to put all of these things into the model. And now all of these things have been modeled before, many times by many people. What is important here is that we have tried to put all of it in a single model. And for a single set of parameters, it should have all of these properties. The reason that it was important for us to do that is that we're not really trying to duplicate what's in the brain. We're hoping that the model would tell us something new about the brain that we don't know yet. And in order for what the model tells us to have any value at all, it better behave like the brain in multiple ways. And so this is why it's important that we kind of calibrate it in many different ways. Now, but instead of giving you a guided tour of the model, what I would like to do in the rest of the talk is to talk about 3 snapshots in this modeling effort. Okay, they are chosen because they are they're quantitative, and they are about dynamics. That in part has to do with the nature of this seminar, but it's also what I know best. So here are the 3 things that I'm going to talk about: local circuits, how cortical cells acquire some of their capabilities. And the last one is to look across a cortical surface and compare that to non-equilibrium statistical mechanics. Okay. So
there's a quick clarification question in the chat. Can you mention if the model included feedback from V1 to LGN?
No, the model does not include feedback from V1 to LGN because it's very subtle. We kind of looked into that. Okay, so it's much more subtle than modeling just the feed-forward volley of information, which is what we are focusing on right now. Okay, of course that's imperfect. It should include. I mean, most of the LGN receives a lot of feedback. We know that, right? But we don't. If you look at how it modulates the behavior, it's too subtle for the kind of the modeling that we are doing now.
Okay, thanks. I should say that was from Eric Cook.
Yeah, yes, no, this is definitely a defect without a doubt. Okay, and so, but most of what I'm going to talk about is actually in the number 2. 1 and 3 are just very short things that I would like to include. Okay, so getting to number 1. Okay, so this is this dynamics of local circuits. I'm using the integrate and fire equations, which I think many of you are familiar with. So basically, we for those of you that haven't seen it, one just forgets about everything else, all the biochemical reactions that go on, and focus on the electrical property of the neuron. So V is the membrane potential, which we have normalized to go from 0 to 1 instead of minus 70 millivolts and so on. Okay, so 0 to 1, easier to keep track of. And this the way what causes the change in the membrane potential are 3 forces. If nothing happens, if it receives no input at all, then it simply leaks back to 0. Okay, And when it reaches 1, that's the firing threshold, it goes off. And the model doesn't really deal, this type of integrated fire models don't really deal with that. So it just gets reset to 0. And the other 2 forces acting on it, one is the excitatory force, which is, this is the excitatory current. And what it does is that it tries to push the membrane potential to this imaginary point, but of course it doesn't really get there because it fires and then it gets reset. And then the inhibitory forces try to push it to this imaginary point, which it also doesn't get there. Well, oh, actually it can get there, this one, it can go below 0, okay? The excitatory and inhibitory currents have, okay, so this is a distance to the reversal potentials, and this is the conductance. And conductance is just that it gets, it's something that just elevates by, for a few milliseconds every time an excitatory spike is received, and this one gets elevated every time an inhibitory spike is received. So for a few milliseconds, this one a little bit longer than that one, but still in the milliseconds range. And so what the neuron does is that it receives barrages of excitatory and inhibitory spikes. So its membrane potential fluctuates, and at some point it goes over. And it's hard to know exactly when it's going to go over because it's kind of getting pushed very hard in both directions. And I want to get this thing farther down. I don't know if I can. Okay.
There's one more clarification question from
Yes.
Leon Glass. Is there a plus sign before G_E?
I have drawn, is there a plus sign before G under this one or that one?
Leon, do you want to turn on your microphone?
Top one.
The top one.
The top one. This, well, it depends on whether you write V minus that or, you know, I hope this is right, but there's only one way to write it that's right, is that it's trying to push it over there. I think this is correct. But minus, I think minus that means that this is trying to push it there, right? Like here, this is trying to push it down to 0. Okay. So I think this is correct. Okay.
Shouldn't the excitatory and inhibitory be different? No?
Yeah, this one is a negative number. This one is a positive number.
Oh.
Yeah, I think that's what. Let me get rid of this floating panel because it's blocking me. Okay. So the main parameters in this local is just x, y, which tells you how much. How big of a jolt that you get when you receive a spike. And this is the very simple picture of the local circuits when you forget about the rest of the, okay. And so now the observation that I would like to make here is the following, okay. There's it's about the currents and firing rates. And so if you look at a cell, a typical cell in this, actually any cell, E or I cell, it doesn't matter. And you look at the amount of E current that flows into it versus the I current that flows into it, it looks like this. In other words, they are these are means, they're very, very close. And they whatever magnitude that is, the difference is really small. And this really small part determines the firing rate. Okay, now here's a proof of that. Okay, what I'm saying is nothing deep, it comes strictly from the integrated fire equation. So the integrated fire equation says that on the left side, if you integrate it and you forget about the reset, but you keep adding, you will get the firing rate, right? Over a period of time, it tells you how many times it crosses threshold, so how many times it's fired. Okay, forget about the leak term, then you get E current minus I current. And here I'm using I current as positive so that I can compare the magnitude. These are magnitudes, right? It should really be, this should be negative, really. Okay. And if you can compare, well, what about E current? Well, you can estimate the E current by the number of presynaptic cells, number of presynaptic E cells, the firing rates of those cells, if you assume that they're more or less the same, the synaptic coupling weight, and the distance to the reversal potential. So you more or less know what these quantities are, not exactly because they move, but you know in the ballpark, you know what they are. And let's say I'm looking at an E cell. Well, this firing rate is the same as that firing rate. So you can look at these quantities and under reasonable conditions, like when there's like a few hundreds, couple hundred of these of E cells, and you use reasonable synaptic coupling, which are guided by data, and you know the distance to the reversal and so on, that's also experimentally known, you can see that this number here is much bigger than that one. In other words, these three things is bigger than one. So not much bigger than maybe 10 times, something like that, kind of order of magnitude bigger. And if something is equal to the difference of two things, one of which is much bigger than it, that means that these two things are really close. And the difference is that. That's the end of the proof. Okay, so this is something that you just read off from the integrated Fourier equation. Okay, now there's a very well-known theory in theoretical neuroscience known as balanced state theory, pioneered by Van Rieseck and Sobolinski about 20 years ago. Theirs is a much fancier thing because there are conditions that they have to assume, and they're going for exact balance as system size going to infinity. Okay, this is one of the best known things in the field. But what I'm saying is something that's much simpler. Okay, first of all, I'm not going for exact balance. I want to know only approximate EI balance, and I claim that follows really just from the LIF equation, integrated Fourier equation. Okay, together with like circuit size, where our circuit size is not 10, you know, it's kind of more like 100, it's not 10. Okay, so these are the only things that I need to conclude the approximate balance. And as a matter of fact, there's another reason for wanting the approximate balance is that I want to know the difference. I don't want it to go to zero. I want to know the difference, because the difference is roughly what determines firing rate. Okay, but this balance is actually not really what I wanted to know. What I really want to, the fact that I want to draw out of it is what I think of as an unreasonable effectiveness of external drive. Okay, so when you have something from outside of the local circuit coming in, is incredibly effective for the following reason. Now, early thinking, especially going back to Hubo and Wiesel, is that in the sensory cortices, most of the near the input to the sensory cortices, things are mostly feed forward. Okay, and that once it gets inside cortex, it just kind of changes it a little bit. But the more modern view is that if you look at in terms of current received, most of it is really lateral, and then next comes feedback. Okay, and feed forward is really only just a very tiny bit of the current. So how does it work? Well, it works because of this. Okay, so the feed forward current only has to change this, and then it would change. It could change. It could tilt the picture very seriously one way or the other. So this is an observation that is made post the model is reflecting a fair amount of this. There's a very little feed forward current. Most of it is coming from lateral, and this balancing is not done by my hands. It balances by itself because of this. Okay, and this way, with a little bit of current, it drives a very big effect. Okay, so this is one of the things that runs through the model. Okay, so this is the end of part one. Now, getting to the longer part is that what I'd like to. So maybe if there are quick questions, I should take that now because I'm changing. Okay. All right. So now the second part, I would like to explain how the cortical cells acquire their ability to detect the orientation of an edge and also the direction of motion. Okay. So just a couple of basic things for people not familiar with the subject. So these are two of the very basic properties of V1 neurons. Is that one is that they have very small receptive fields. Meaning that the piece of the visual field, the part of the visual field to which the neuron has direct feed-forward information is very small. So I'm going to say kind of informally that this neuron just sees a very small piece of the visual field in front of you. Kind of think of it as like a quarter the size of the moon. I like to think about the moon, quarter the size of the moon, like that. Okay, and the second is that there's a retinotopic map in very much the same way that there's a map of your visual space on your retina. That whole map is passed to V1. So there's a kind of like a correspondence between the location in V1 and the location in the visual field. Okay. Now, getting to the two properties that I would like to explain. The first is orientation selectivity. This is one of the primary functions of V1. So what the most basic, what all that it says is that each neuron has a preferred orientation. So if you take a bar and you move it along like that, the neuron may or may not respond. You tilt it, maybe it responds more. This one it likes, so it's firing a lot. And then now it doesn't like it, again So people make these tuning curves. So this is the angle of the bar, the orientation, and it prefers some orientation much more than others. They're not all that clean. This is a particularly clean picture that I just grabbed out of the internet. Okay, but anyway, this is one of the properties that I would like to explain. But the one that I really want to explain is this one, is direction selectivity. This is pretty well understood. This is not. This is a kind of a new work that I would like to share with you. So what is direction selectivity is that in addition to having an orientation that it prefers, the bar could be coming this way or the object could be coming that way. Okay? And the neuron has a very specific preference. It just likes one way and doesn't like the other way. Okay? Most neurons have that kind of preference. So where do these things come from, right? So the first thing to know is that LGN, okay, has no orientation selectivity or direction selectivity. So the cells in LGN don't distinguish, have no preference for orientation or direction. And there is nothing between LGN and V1. In one synapse, it just goes there. And yet these cells haven't. So where did it come from is what I would like to explain. Okay, so first for orientation selectivity, there's a very well-known hypothesis of Hubo and Wiesel, who observed very early on that each neuron in V1 in the input layer is connected to groups of LGN cells that form either 2 or 3 rows of on and off. And these rows have certain inclinations, and these inclinations would determine the preferred orientation of the neuron. So they observed this, and this picture has pretty much been borne out experimentally in receptor field mappings. Okay, so everyone, when I read this, and this is in every beginning neuroscience text, and everyone seems to find this very obvious, except for me. I didn't really understand it, so I tried to look into it a little bit more to try to understand this better. Okay, so here's how the structure and dynamics of LGN works. Okay, so this is one sheet, one of 6 sheets in LGN. We only have to look at one of them. And LGN is relatively straightforward. There are 2 types of cells, on cells and off cells. They also have very small, very localized receptive fields. Okay, and the on cells are excited when, so it only sees like some little tiny region in the visual space, and the on cell gets excited when in that region it goes from dark to light. Okay, so it detects the changes in luminance, then it gets excited. And the off cells are excited when it goes in the opposite direction. So, and these cells are laid out in some kind of mosaic into two networks that are fairly even, but not completely evenly, kind of more or less like the way I have it drawn. So they pass on the information to cortex. So a little bit more information on LGN is that the input current, this is, I didn't invent this, people have been using this for a while. So the input current has some background one, but mostly is this part. So this is the light intensity map. So it's a convolution of the light intensity map that it receives with a spatial current, with a spatial kernel and a temporal kernel. Okay, so the spatial kernel is basically like a Gaussian. So this is a function of radius. It's basically like a Gaussian, actually more like a difference of 2 Gaussians. There's some surround effect, but it's not so important to us. So I mean, just think of the spatial thing as just summing up what's nearby. Okay, but what's going to be very interesting for us is the temporal kernel. So the temporal kernel has a funny form. So when you integrate against a Gaussian, we all know what happens, right? You just basically average the stuff in between. But what does it mean to convolve against something that looks like it has a sine waveform? It's basically you're taking a derivative, right? So that's why LGN cells are change detectors. Okay, so if you give it a gray background or dark background or light background, the cells are not going to fire. In this magnet layer anyway, they're not supposed to fire, but instead they detect changes. That's why it detects this change in luminance. So this kernel is upside down for on and off, and I'm drawing it for let's say on. Okay, so this is how LGN cells work. And so we're trying to put all of this into the model. And this slide is, I'm not going to get into so much, but just to tell you that, and we quickly ran into our first crisis in this modeling project, was that we discovered, digging into the literature, that LGN is extremely sparse. Okay, in the magno layers, that looking into these papers that actually have been around for a while, we discovered that there's really only about 10 LGN cells for this area, which is like a quarter the size of the moon. It's like 5 on and 5 off. That's almost scary, right? It's very, very sparse. Okay, so when it's so sparse and you're supposed to form something like that, well, that's a problem. Okay, that there are many constraints. First of all, they cannot reach too far. There's many sets of experimental data here that tells you that you're supposed to choose from something on the order of 15, 20 cells and form these rows and that are parallel of on and off. Okay, that's a big problem. How do you fit all of that in? There's a combinatorial geometric problem that kind of we ran into, constrained by this data. You can see, right, I barely fitted 2 rows of 3 in. But anyway, and you're supposed to do it around the clock, right? Because they share the same pool of cells. You have to be able to make rows that are parallel in all different directions. So that was a problem. Anyway, to cut long story short, it can be done barely, just barely, but not without a whole lot of room to spare. And they look kind of more like this. This is 2 rows of two columns off and on. And this one has 3. They look more like that. Okay, so going on to explain, but how does it work? So here's my attempt to explain how it works. So let's say that I have a V1 cell and it's connected to these 4 LGN cells, right? These 2 on here and 2 off here. Okay, so it's optimally driven when you're sending along a drifting grading. It's optimally driven in response the most when the drifting grading is aligned with these directions, so like that, okay, and that the spatial separation of this is roughly the spatial separation of the light and dark. Okay, and this is because imagine the situation where this guy is like here, right? So it's going from let's say the grading is going this way. So this guy here is now changing from this guy's here is changing from dark to light, and these guys here are changing from light to dark. So all 4 are excited simultaneously. So when the grading is vertical, all 4 are excited simultaneously. But if I rotate this thing by 90 degrees and have a horizontal grading that moves up, then at all times half of them will be excited and half of them are not. So the story is that when it's optimally driven, the pattern, the spikes that the V1 neuron receives would come in bunches, that they're all excited together. Nobody's excited, all 4 are excited, nobody's excited, alternating like that. And that elicits a very big response from the V1 cell. Whereas if you are in the orthogonal setting, then they come more or less evenly and it elicits a very weak response. Okay, now in the early models of the visual cortex, people often model the parts that are optimally driven as receiving many more spikes. Well, think about it. If the cell is hooked onto these 4 LGN cells, it's the same 4 LGN cells. Each one of the LGN cells does not see any orientation. It's going to respond exactly the same way to whatever grading you give it. The V1 neuron cannot get more spikes, depending on the orientation of the grading. They always get the same number of spikes. It's the pattern that's different, and that's what leads to orientation selectivity. But why is the pattern mattering so much? Is that if they come packed together, okay, it has nothing to do with the periodicity. It's really the fact that concentrated spiking is much more effective in eliciting spikes, because you drive it up. Okay, so you get a jolt from LGN, it leaks out. Jolt, leak out, leak is coming from this term, go up, leaking, go up, leaking. So all that you have to do is to drive it past threshold, and then the story starts again. Okay, so if you don't have any time to leak, you're going to drive it up. I'm exaggerating here. Here you drive it up and then it leaks most of it away, drive it up, leaks most of it away. It's not responding. Okay, so this is kind of how I understand the dynamics of how this works. And in our experiments and as well as models, the LGN to cortex, the current from LGN to cortex comprises only about on the order of 10% the amount of current, total current that is not of lateral, of the total current received by the V1 cell. It's a very, very small fraction of the current comes from feed forward. And yet it's so effective. I mean, this is the basis on which everything we see is dependent on this. And why does it work? Is I think of this as the unreasonable effectiveness of the external drive. So it's a little bit of drive. It's not even different in the number of spikes, just the patterns being more bunch of than others. And that's how we tell orientation according to the model. Okay, so I'm going to direction selectivity if there are quick questions. Okay, so now what is direction selectivity? Is that suppose you take
We actually have one quick question that's just come in from Suresh. Suresh, do you want to just ask your question?
Yeah, I was curious because you're using this coincidence detection mechanism. Does it make verifiable or verified predictions for the temporal frequency dependence of orientation selectivity? Yeah,
sorry, exactly what was the question again?
So if the grading is moving at different speeds,
yes, it depends on that. It's going to depend a lot on all of those things.
So that means the orientation selectivity may depend upon how fast the grading is moving.
The orientation does not depend on it, but it only sees a certain range of temporal frequency, and it has no response outside of the range of temporal frequency and a range of spatial frequency.
Okay.
And the strength of the response is also different, but the orientation does not change. Okay. Okay. So direction selectivity is when there is, so let's assume from now on that my neuron prefers vertical. Okay. So that the gradient can go this way and goes that way. And it's called direction selective if it favors one over the other. Okay. And so the neural basis, the direction selectivity is the neural basis for motion perception, which is developed much more further down in MT. This is a property that it's already detected in the input layer of V1, discovered in the 1960s. And for a number of proposals have been made, but no satisfactory explanation has been given up until recently for the macaque V1. Okay, so for some experimental facts, it is found that in the input layer, more than half of the simple cells are very strongly selective, direction selective. Now, again, I will remind you that the LGN cells are not direction selective. They're not even orientation selective, so they cannot be direction selective, right? So where does it come from? Okay, and and it's not something like a random thing. Okay, the same neuron will consistently prefer the same direction. And this is broadband in terms of spatial frequency and temporal frequency, meaning that it's not just for one special one, but when a neuron doesn't respond anymore, then of course there is nothing to speak of. But within that range, it always prefers, very consistently preferring the same thing. So we try to propose an explanation. There's a new paper by the four of us. And the explanation that we propose is that even though individual LGN cells are not direction selective, if you sum over the LGN afferents to a particular V1 cell, it becomes that summed response is orientation selective. And so let me explain this like that. Okay, so instead of two rows, let me simplify and just think of a pair of on-off. You think of each one of them as representing a row. Okay, and that way I only have to think about two kinds of gradings, left, right. Okay, with my on-off cell placed like that. And then the response is given by the sum of these two, the response of the on and the sum of the off, where each one, and I'm going to cheat one more time, that I gave you this formula as representing the input current to LGN. I'm going to think of that as the output as well. It's not quite right, but it's not terrible because LGN is fairly linear. Okay, so it's a cheat, but it's very convenient for helping us understand what is going on. So this is the idealized setting that I'm looking at, two cells, two gradings, and on and off given by this. And I'm even going to just focus on the temporal kernel. Think of the spatial kernel as just soaking up stuff nearby. Okay, so first thing to observe is that if this is a grading, then this is a sine function. And if you take a sine function and convolve it with a kernel, a reasonable kernel, what you get is another sine function with amplitude is changed and there's a phase shift. Okay, so that way, when these responses are in the form of a sine function with a phase shift and changed amplitude. Now, so the key to doing this, and this is not a new idea because it's already in the literature. We just kind of made it work. Okay, so so delta phi is the phase difference of on and off for a particular grading. So if I give it one grading, because the information would arrive at this cell at a different time than that cell, the two cells would have a phase difference. Okay, now because on and off are opposite, I have to fix a notation. So let me declare this phase difference to be 0 when both of them, the sine function is peaking simultaneously. Okay, so I'm going to say that it's 0 when both of them are at max. Okay, now so obviously if you add the two, it's max when the phase difference is 0. So now if you look at any if you look at the two gradings, so then you have two phase differences. All you have to do is to look at which one has a phase difference closer to 0. The one that has a phase difference closer to 0 is the one that's going to have a bigger response, and that's what the cell prefers. Right? So the easy fact is that if you use the same on kernel for same kernel for on cell and for off cells, then the two phase differences are the same, whether you use a grading from the left or from the right, proved by symmetry. Okay, you just reverse everything and then write your proof all over, and it will be identical. So what this says is that DS comes from broken symmetry caused by different time kernels. Okay? Because if they were the same, you can never have other things being equal, right? You can never have a DS. You can never have a preference. These two would be the same. Okay, so the problem now is not so much that this is a fairly easy observation, but the harder part is to look for biology explanations for these differences in time kernels. I don't get to go and choose two kernels by hand to make them different, and so so we found two mechanisms. One is a time delay of a few milliseconds in the arrival of the on signal. And this is a well-known fact in neuroscience. In the retinal circuit, there's a sign inversion for on in the retina, causing the on signal to arrive a little bit late. So this is a well-known fact. Now, if you think of this signal as delayed, then when it's coming from this side, it's going to be the arrival time from off to on is going to be longer. Whereas for a signal coming from this side, if this one is delayed, it's going to be shorter. So the time difference between the two. So in other words, I've broken the symmetry and it works. However, it does not work at higher temporal frequencies. Sorry, it works at higher temporal frequencies, but does not work at low temporal frequencies. The reason it does not work at low temporal frequencies is that if this difference in time is very long, and you only offset it by a few milliseconds, it's just not going to do anything. Okay, so we need another mechanism to explain it at low temporal frequency, and this is what we found in the data from Reed and Shapley from nearly 20 years ago. So looking through the data, what we found was that the time kernels were a little bit different. They're not dramatically different. This is the on ones that sometimes a bit taller than the off ones. Okay, the white one is the on, and I've plotted both to face the same way. They should be opposite, right? Yeah, just as easier to compare. Okay, so we notice that there is a difference in the on kernel versus the off, and this is enough to produce the phase shift at low temporal frequency. I'll let you figure that out, but I want to give you a little proof of why this little bit of difference will work. Okay, the thing is that when it's so if I think of the on kernel as basically, well, there's a time delay also, right? But there's an off kernel plus a positive part, right? Because it's taller, so there's a little more extra bit that's positive. Well, you think of the signal as sine. Okay, so what's the response? If it was just the off kernel, I'm cheating now. I told you that it's like taking a derivative, so it's like a cosine, right? Because it's like taking derivative. But then what about this positive part? This positive part is like a convolution with something that's all positive that gives you a sine. Well, if you add a sine function to a cosine function, you shift this phase. That's the mathematics behind it. Okay, so these two mechanisms together produce very good results in the summed input from LGN. Now, I said it produces direction preference, but which direction? So here's something that can be proved, is that, well, it actually has to do with you have to compare these two numbers. This D is a distance between the on and off cells measured in degrees in the retina, okay? And then there's this big D, which is the distance between two bands, okay? So what we found, and this is a mathematical fact, is that when D is smaller than, little d here is smaller than big D over 2, it prefers one direction from off to on. At this point, it switches and prefers the other direction. And then at this point, it switches again. So every big D over half, it switches. Okay. And this is a mathematical fact, which is quite easy to prove. It basically has to do with the fact that, you're looking at faces, that it's like 2 points living on a circle. If you have 2 points on a circle, as they get increased, the distances, if they move apart, their distances increase. At some point, the distances start to decrease again. Okay, so it has to do with that kind of a thing. So this is so we have to say, but that now that's a problem, because in experiment I just told you there's no switching from of preferred direction for the macaque. Okay, so what came to our rescue is the following. If you look at the range of where there is any response, the macaque actually does not respond when the spatial frequency is more than 5. Well, we're looking at things at about 5 degrees eccentricity. And what you see is that at those locations, it does not respond to a spatial frequency more than 5 cycles per degree. Okay, and that translates into the following. For as long as this little d is less than 0.1 degree, then it's not going to switch. It will all be contained in one interval. And then that happens to be consistent with anatomy. So we're happy that we didn't do something that contradicted the biology. In fact, it agrees very well with the biology. Of course, these numbers are they scale with the receptor field size. So, but this is at one particular location. Okay, so we've done this. So what we have shown is that the summed feed-forward LGN inputs have direction selectivity. I want to stress that this does not mean that the cortical cells have direction selectivity, because after the signal, which is direction selective, reaches cortex, cortex has most of the currents happens there. You don't know what happens to it. It may destroy it, it may average it out, different things could happen. So now we have to go to the model to look more clearly to see what happens. And this is some work that we've just completed. So this is the comparing model result with experimental data. So first I have to tell you that direction selectivity is measured in terms of, one way of measuring it is in terms of what is called pref over op, where pref is the firing rate in the preferred direction divided by the firing rate in the opposite direction. But firing rate is not measured in mean, is measured rather in the first Fourier coefficient, because it is the F1, is the amplitude of the sine wave function that elicits the spike, as we talked about a little bit earlier. So DS is measured as pref over op. Okay, so how much more does it prefer one direction over the other? And here's a little figure from our paper. Green is data, black is model. And so, for example, let's take the number 3. So let's look at the fraction of cells where it prefers one direction 3 times more or more over the other. For data is about 58%, and the model was like maybe 56 or so. And I think these curves are fairly close. These are for simple cells, and those are for complex cells. And of course, there are knobs in the model that I could tweak, but it did not involve, really doing terrible things. You just move something a little bit up or down, and this is what the model says. So what we found in the model was, in fact, that the cortical DS is bigger than feed-forward DS, something that at first surprised me a little bit. Okay, so what do I mean by feed-forward DS is that the DS of the directions, the pref over op, right, of the summed LGN input. So the input received by a neuron is this one, and this is what the neuron actually responds, the response of the neuron. So we were worried at the beginning that this one might be small, even though this one is solid. But what we found is the opposite, that the cortical response is actually bigger. Now, there are all kinds of conjectures in the literature about how special connections that promotes the direction selectivity within cortex. I assure you that there is none in our model. Everything is done completely blindly with no regard to which neuron is going to prefer what. Okay, so, but why is that true? And here's a proposed explanation. The proposed explanation for us is that dynamical interaction of the feed-forward current with the intra-cortical current is a very, very generic explanation. Now, this is what happens in the model. I don't know that this is really happening in the real brain, and I'm putting this forth as a testable prediction. Okay, so here it goes. Why is that so? Why is it that cortex actually magnifies the selectivity. Well, we said earlier that it comes like this, it's bunched up and then blank, and then a bunch of LGN spikes blank. If you look at how the membrane potential of the V1 cell does, it's going to follow this. When the spikes comes, it's closer to the spiking threshold. And when it's blank, it drops back down to farther away. So there is a phase in the membrane potential of the V1 cell. Point number one. Point number two is that if you look at the intra-cortical currents, so this is the same phase as what you see here, the same x-axis as what's see here. This is amplitude, F1. They're all anti-phase. The point is that intra-cortical currents are anti-phase to LGN. Okay. Now, this is not something that I did. I didn't do anything to it. It works that way, and I claim necessarily so, because again, if you look at the excitatory current, it's equal to the conductance times this quantity, the distance to the reversal potential. So for E, the reversal potential is up here, right? So of course, it's biggest in the middle, in mid-phase. So it's biggest in mid-phase. And if you do it for I, it's the same thing. It's also biggest for mid-phase. In fact, it's even more pronounced. But then your brain has to take a couple of minus signs around. So I didn't write that out. But this is both mathematically verified and also numerically verified that intracortical currents are anti-phase to LGN. So why is that relevant? That's because if you look at the feed-forward DS is preferred over OP for LGN. But for cortical DS, you have to count the cortical current. And because they're anti-phase, it's a subtraction. So you have the preferred for LGN minus whatever preferred for cortex, and opposite LGN minus opposite for cortex. Okay, and it turns out that these two quantities are very similar. Okay, so what happens is that this is for LGN, this is preferred. You have a big F1 divided by op. So DS is this height, this amplitude divided by this amplitude. After you subtract, it becomes this divided by that. That's when you're subtracting off something that the two that are being subtracted are more very similar. Actually, you're even subtracting a little bit less over here. But the point is that the denominator becomes really tiny. And so and when the denominator becomes tiny, the cortical DS gets big. So here's a lesson learned from the model. I don't know if this is true in the real brain. It's a testable prediction. I mean, people have thought that feature selection comes about when cortex magnifies things in different ways. Actually, here it seems to have selectively, by making the denominator small, it also can magnify the ability to detect direction very well. So this is what we found. And I'm going to go to the third part, which is very fast, is that, okay, so this is a model you have seen before. I want to show you something, which is, okay, so this is a real imaging of a real cortex when you put the same color for neurons to prefer the same orientation. So you can see that they are bunched together in orientation domains. These are called orientation domains. This is optical imaging, okay? And so in the model, it looks like this. I have my 9 hypercolumn. Each one, I've divided them into different regions. And for each one, if it's assigned an orientation, which I'm going to hook onto the LGN following the rules of Hubo and Wiesel, right? So I'm going to hook onto them but this is the intended orientation. Nobody says that it's actually going to happen that way, but then it does. And so these are activity maps. You can think of them as kind of like some version of an fMRI, but on the neuronal level. Okay, so I can see neurons actually happening. There are movies, but I won't show that. Okay, so this is 0 is vertical. So let's compare this. So when I'm given a vertical grading, I go to this place. I look for the places where the intended grading is vertical, which is these 3 diamonds and the 3 half diamonds. And then I go back, I look back up there. Hot colors are high firing, cold colors, low firing. And indeed, these are the regions that are firing the most. Okay, and this is E and this is I. E and I always co-vary. So they come up together and they go down together. And you can check with what about 45 degrees? Okay, then I come to my key and say, well, I don't have 45 degrees here, but I have 30 and 60. So it must be these 3. And lo and behold, It's this part that comes out. Okay. Now this thing is actually a really scary thing to do, because you have like these 40,000 neurons of which you have no control, right? You just hook it up to the LGN and it produces whatever it produces. But what I want to emphasize is that these things, the network, both for LGN and for V1, are both spatially very homogeneous. Okay? There's nothing so inhomogeneous about it. But the stimulus, so in particular, each grading affects this, the response very differently because of the different wiring. Okay, so that leads to the last idea that I would like to share with you. It's the rough analogy with non-equilibrium StatMech. Okay, so in StatMech, if you think about a piece of homogeneous matter, you model it with a very homogeneous lattice or crystal type structure, and the cortical surface is also spatially homogeneous. Okay, within one layer. I'm talking about one layer only. Okay, it's also spatially very homogeneous with isometric connections. In mathematical terms, we call this translational invariance. Okay, but just like in StatMech, you get the inhomogeneous behavior through coupling to unequal heat baths, and here you show different stimulus and the different wiring causes an inhomogeneous. Is the input that it's actually, I should say, is caused by very inhomogeneous inputs. Okay, so I actually should have said that I like you to keep this picture in your head as I go through this. Okay, the network is completely homogeneous. The output is not, because of that. Okay, now in non-equilibrium StatMech, if you force the system out of equilibrium but then leave it alone, it goes to a non-equilibrium steady state, and that is obtained by balancing of heat fluxes in the neuronal system. It's balancing excitation inhibition together with the inputs. Okay, and cortex is without a doubt out of equilibrium when driven. Okay. Now, but there's another way of understanding when in non-equilibrium StatMech. If you think about a system is so driven out of equilibrium with fluxes flying everywhere, it's impossible to understand. But one way to understand it is that locally, the system is actually on some mesoscopic scale. The system is actually in equilibrium, and we know equilibrium StatMech very well. We know what the distributions look like. Okay, and the same is true in this neuronal system. Moreover, we could think of the non-equilibrium steady state as a lot of local equilibria sewn together, and the same is true in the neuronal system. So the main takeaway from this last discussion is that in non-equilibrium StatMech, we can think of non-equilibrium steady states as a collection of local thermal equilibria, which are very well understood, and they depend on a finite number of parameters. And so now you can focus on this non-equilibrium state as how to balance the heat fluxes, how you sew all these equilibria together. Identical picture within a cortical layer, you have local neuronal equilibria, also defined by a finite number of parameters, and it's not balancing heat fluxes, but balancing excitation inhibition. And what is in progress now is that these ideas are being used to build the next generation models where we scale up to a much larger piece of cortex and more efficient, easier to handle models. So here's my one-page pictorial summary. So I talked about the visual cortex. Most of the things I've been telling you come from a model that looks like this. Most of the LGN input layer. This single model has been shown to replicate most of the properties in the input layer. And so now it's time to ask it to give us back something new that we don't or we didn't already know before. And so venturing into less charted territory, the first observation is this very unreasonable effectiveness of external input. Then I talked about origin of direction selectivity as coming from a slight offset in the temporal filters in the on-off pathways, together with the way that feed-forward and intra-cortical currents interact. And finally, this is my attempt to build the next generation model that's bigger and better. And these are the people that I've worked with. Most of the work that I discussed with these three, Bob Shapley and Mike Hawken, Logan Charaka, these two are closer to being experimental neuroscience. They are neuroscientists and mostly experimental. And then the last part of the new model is with these two. And the work is supported mostly by NSF, experiments by that, a bit of Schwartz Foundation. Thank you. Okay. So maybe I put it back to this page, okay, so people can ask questions, easy to point.
Thank you very much. A wonderful.
Thank you. Thank you for listening.
Are there some questions for Dr. Young? Oh, Eric.
Hi, yeah, great. Thanks for an interesting talk. And I like these models that try to capture some of the experimental realism of what's going on. When you talk about balanced EI, I mean, another prominent cortical model we hear a lot about is the Heeger divisive normalization model. Are you guys, or is this different ways of talking about the same sort of?
I don't believe so. I think the normalization model has more to do with well, they may be related, but what I have here, it does not involve any kind of dividing by anything. Okay, it's really just the integrate and fire equation that says that if you look at those two terms, it has to come out that way. Okay?
But do your conductance terms produce sort of a divisive effect on the activity of your integrate and fire models? I'm just trying to sort out these different models. So, you know,
not the way we go about it. Whether it ultimately boils down to the same thing, probably yes, in the brain, right? But what this says is that if you drive E high, it's automatically I is going to get high. If one is low, the other one is going to get low, and the difference is going to reflect the firing rate. So now I didn't divide by anything in particular, but if you're saying if the underlying thing that causes these things to happen, are they the same or not? I don't know.
Suresh?
Yeah, thank you. That was a great talk. Actually, my question is very closely related to just formulated slightly differently.
We lost you, Suresh. We lost you for a second or two. Can you just say that again?
My question is very closely related to Eric's. It's just it's on the same line, along the same lines. So you highlighted all these network features and predictions, and it was really what was really interesting was that they were intuitively understandable, right? So you were able to communicate them. So in a sense, is there anything in this model that's not produced from, say, a rate model with linear filters and some simple nonlinearities, right? And a sort of related question to that is, how easy is it to capture these effects with this nonlinear spike-based, conductance-based integrate fire model? So if you change the hyperparameters or various EI assumptions, does it suddenly break down, right? So how much parameter sensitivity do you have? Or is it very robust? So what can we learn about all these multiple parameters that are sitting in your model about which you've made choices?
Okay, so did you ask actually a bunch of questions for comparison with the rate models? In rate models, there are many assumptions. You have to assume how the neurons interact. You have to assume some gain function. And all these are assumptions that are made. And whether or not you can make the assumptions correctly to reflect all of these things, maybe. I mean, most of the rate models around do not claim to be realistic in that kind of way. But now this is about for things with regard to firing rates. Now, when it comes to temporal properties, for example, the things that are a little bit more delicate, the patterns, your rate model can of course also be rigged to produce those things, but your rate model is going to become more and more complicated also if you try to accommodate those things, right? Okay. If you just have a single rate, you're not going to see these properties, right? So like because they come in different temporal scales. Okay, so that's one answer to the question about how stable the parameters are. So for this model, with everything together, is too complicated to search all the way through. We have actually done other studies where we focus on smaller things to look at what the set of viable parameters look like. Okay, so for example, we've just completed a project. I think it's actually on the bioarchive now. Really searching through all the parameters that we include. That's like somewhere between 5 and 10 of them, 7, I think, to be precise. So to see when can we, when do these things come to a balance? When do they not? So the thing is that if you define a good region to be the regions where it fits more or less experimental data, it's a codimension 1 manifold. It's a thickened up codimension 1 manifold. The codimension 1 coming from EI balance. So it's actually, so is it very delicate or is it not? Right? I don't quite know how to answer that, right? If you look at a codimension 1 manifold, like 6-dimensional manifold sitting in 7-dimensional, of course you can get off of it quite easily, but there are also many directions to move and you won't get off of it, right? So it's thickened up. It's not really a 6th dimension, but that's kind of the nature of what the parameter set looks like.
Great, thank you very much. Yeah, thanks.
Leon.
So thanks very much.
Hi, Leon. We met in Snowbird, remember?
We've met a couple of times. I met you in the halls of NYU once.
That's true too.
It's fascinating how you can put these very simple elements together to get such interesting properties. You haven't said much about visual perception and how this can lead to visual perception. And I'm thinking about 2 aspects. One is any visual effects that you particularly have insights into as a result of doing this analysis. And also, I'm always concerned about the role of eye motions in people when we're looking around.
Yeah, the things that you're asking are the things that we aspire to do. But the reason that we're able to explain these things so relatively well is because they happen at the beginning. And so there are very few things in play. Once it moves even further down in the visual cortex, then things become a little bit more complicated. Like in MT, people don't really understand very well what is going on. And then it's not just the visual cortex that's involved in perception, right? It's involved with the rest of the brain. So we aspire to push these things farther to see if we can explain some more of it. But this is simple because is at the beginning, really.
Terrific. So, do you have any comments to the people who are making the Blue Brain project and these highly detailed models?
I think I think we need to understand these things on all levels.
Okay.
No? So that maybe when we put it all together, we can understand it on all scales and all levels. But...
Okay, great, thank you.
Well, I thank you very much. I think we're coming to the end. Yavar?
Yeah, okay. Thank you so much for the great talk. And yeah.
Yes, it's a real pleasure to have you here today.
Thank you all for coming.
Thank you so much. And hopefully we'll be able to see you in Montreal in another year.
I really would like to come.